So welcome to our webinar. My name's not Marlies Reining. I am standing in for Marlies today. My name is Francois Retif. Some of you may know me as a sustainability engineer, but today I'm a volunteer here at the Regenerative Collaborative of SA. And we're talking about next generation hot water systems today. We promise not to make it too technical, just the right amount of technical, but entertaining and informative. Okay, so about the RCSA, the webinar is organized and brought to you by the RCSA, the Regenerative Collaborative of South Africa. It's a non-profit organization focused on transforming the built environment into a regenerative one. We promote strategies and approaches that bring regenerative design and construction to life. We work collaboratively to inspire, educate, create awareness, and contextualize regenerative built environment approaches to the South African context. We make an effort to showcase local projects, local people, local companies, and are aligned with our goal, creating a regenerative future. In case you've missed any of the previous webinars, check out the YouTube channel. There's recordings from the past 4 years. And while you're there, please show your support by hitting subscribe or giving the videos a like. It will be really appreciated. You can also follow along on the other socials. So Eventbrite, LinkedIn, YouTube. Yeah, please stay connected to get the latest information from us. And you can also reach out on the email address on your screen. If, like me, you'd like to volunteer, as I am today, we're always on the lookout for passionate team members. Whether you bring social media savvy skills, administrative skills, you know someone interested in an internship, we'd love for you to join us. No deep expertise in regenerative buildings required, just passion and eagerness to join. Okay. So onto today's webinar, focuses on next-gen hot water systems, specifically heat pumps and PVT, photovoltaic thermal technology. While heat pumps are increasingly recognized, many still don't understand how they work or why they outperform traditional boilers. And PVT offers a groundbreaking innovation by combining electricity and hot water production in a single solar panel. So on that note, just a word from our sponsor, Solarus. So yeah, we're grateful and excited to have Solarus as a sponsor. The company is a pioneering force in renewable energy, redefining how businesses and industries harness the power of the sun for a sustainable future. Solarus stands out by transforming abundant sunlight into reliable, high-performance power solutions tailored for commercial and industrial applications worldwide. What sets them apart is their hybrid PVT technology, an innovative system that not only generates electricity, but also captures heat, making it the most efficient use of solar energy for businesses with high thermal demands. Industries that rely on hot water, process heat, or space heating, such as manufacturing, hospitality, healthcare, and agriculture, are already seeing the benefits of this dual energy system. By optimizing both electrical and thermal output, Solarus delivers significantly greater energy savings and a faster return on investment compared to traditional solar. Those integrating PVT are now gaining a long-term advantage in operational efficiency, cost reduction, and sustainability compliance. We've been impressed with how Solarus has built its reputation on quality and reliability. Their commitment to sustainable practices is evident in every aspect of their work. With Solarus, businesses can drastically cut energy costs, reduce fossil fuel reliance, and take control of their energy future before the rising costs of regulations force reactive decisions. As the energy landscape evolves, staying ahead means choosing solutions that offer more than just electricity. The shift towards integrated solar thermal technology is already happening, and the businesses adopting it today are the ones securing their competitive edge. We encourage you to explore more about what Solarus has to offer on their website, where you'll find detailed insights into their products, success stories, and innovative hybrid PVT technology driving their systems. Today's session will provide an in-depth look at how Solarus is setting a new benchmark for healthcare, industrial renewable energy, and how the company's that act now will be the ones leading the way. Thank you to Solaris for sponsoring this webinar. We have on the webinar today, Ingo Hamman will be our first speaker. Ingo's as a seasoned managing director and dedicated heat pump enthusiast. Ingo brings a wealth of expertise in renewable energy and sustainable building solutions. With a career that spans northern Germany, China, and southern Africa, he has consistently championed innovative product design and cutting-edge technology to minimize environmental impact. Deeply committed to promoting energy independence through renewable sources. Ingo's passion is evident in his personal journey with heat pump and solar installations over nearly 2 decades. His focus on teamwork, continuous learning, and sustainable practices has made him a driving force in the green building movement. Yeah, thank you. It's good to have you here, Ingo. Your bio is quite something, and it's and you're quite a well-traveled man.
Yeah.
Okay, go ahead.
It does show how old I am. That's the only thing.
Excellent. So Ingo from Steve Ultron, and then our second speaker, Michael Boyce. So Michael Boyce is a hot water specialist at Solarus Smart Energy Solutions. Michael designs and implements renewable energy solutions across South Africa, from hotels and hospitals to breweries and food processing plants. His innovative work ensures these industries have a consistent, reliable hot water supply through advanced solar-powered systems, reducing dependence on an unstable power grid and lowering their carbon footprint. With a strong background in business administration and management, including a bachelor's from Regent Business School and a diploma from UCT, Michael excels in team motivation, clear communication, and critical thinking. His passion for sustainability and innovation is driving the transition to a cleaner, greener future. Great. Thanks, Michael. I don't know if you want to put your camera on and give a wave.
How's it, guys? I'm not as old as Ingo, but I'm here.
Cool. Michael, you're from Limpopo, right?
Yes.
So also very well traveled is Michael Boyce now. Great stuff. Okay, so we're gonna head on to our first presenter, which will be Ingo. Ingo, you can share your slides and we can move into your presentation.
Okay, thanks for having me, guys and girls. Let's dive into the heat pump mode. As you know, I'm working for Stiebel Eltron, and our company is in the market of heat pumps since 50 years. You can see that here in the middle. The company is 100 years old, as it states here. So a lot of experience in heat pumps and other hot water devices. And every 15 seconds somewhere in the world, there's a Stiebel Eltron appliance getting into work mode. It's quite impressive in 120 countries, and I'm in one of it in South Africa, and I'm happy to be here. I don't want to bore you with the company details. You can find that online or on my LinkedIn. We will go through the basics of heat pumps and how they work, and then the most important stuff, the COP, the coefficient of performance, and the seasonal coefficient of performance, and what's the difference and why it's so important. Then I brought some project examples and how we gonna heat domestic hot water, and at the end, I'm gonna hand over to Michael, and we combine two systems. We have some running already in South Africa, which is quite interesting to combine the PVT work and the heat pump business. Okay, the basics. How efficient are heat pumps? They're really efficient, but how? It shows here up to 350%. Sounds weird, but I'm gonna explain you in a second how this has been done. And heat pumps are using renewable energies from air and water or ground. So basically groundwater or via convectors, which are sitting in the ground like piping or other heat exchangers. The most important part is it depends where you get your electricity from, because all our heat pumps are running on electricity. And if you get it from a PV or PVT system, the heat pump can run normally or nearly for free. We get into detail a little bit later. So all altogether. You have lower energy costs if you're using a heat pump to heat your hot water. You can also do heating and cooling, but today main focus is on heating your hot water demands. That will benefit you in having a lower CO2 emission. You know, we're all facing a climate change right now or since years, and it's getting worse. So it's better to lower CO2 emissions. That's why I love online meetings, because we don't have to travel that much. It's eco-friendly, of course, and it's really innovative. Every year there's new ideas coming. But let me tell you, everyone who is here today in this webinar, you have a heat pump at home. It's your fridge in the kitchen. I think it's in the kitchen, or if you have a wine cellar, maybe there's one too. So if you touch the back of your fridge, it's always warm. And this is the energy you are creating by pulling the warm energy out of your food or beer in the fridge. And you can basically heat your kitchen with warm vegetables, if that makes sense so far. But I'm going to show you now how that works. So imagine now the heat pump is just a red box or a black box, right? You need some electricity to run it. There's gas heat pumps in the world, mostly in Japan. They are good in this. So you need some energy to run the heat pump, yeah? So imagine now you put electricity in here, preferable from a solar system, from a photovoltaic system, because then the energy is for free. Then you add to this mix some energy which is free in the air. You know that big star we call sun? It is warming up everything. So there is warm energy. And what we do now, and why it's called heat pump, we are pumping energy from a lower level of temperature and pressure to a higher level of temperature and pressure. And with that, we can create or generate hot water or anything else you want to heat. It's basically, talking like my old physics teacher, it's an energy transition. So you're just moving energy from one side to the other side with the help of something, which is in our case a compressor. You can also transfer energy if you rub your hands and then they are getting warm and you touch the cold surface. This is also energy transition. And then on the other side, as I said, you can heat up everything you want or cool down everything you want. This is the basic principle of the heat pump system. So now you need some equipment to it. You have the compressor, as I said, and to gain the energy, in this case, the air source heat pump, we want to have the energy which is in our environment, like in the outside air. Even down to minus 20 degrees, there's still energy. And who knows Mr. Kelvin? Yeah, Lord Kelvin, he found out that only by minus 275 point something degrees, then there is no energy left anymore. So we have a special gas in our heat pump, which is called refrigerant. They are different in the market. And this is able to get the energy from the environment, because it's always colder than the environmental temperature we have, and then it is changing its appearance from being liquidish a little bit, and then it becomes vapor or hot gas at the end. And this hot gas we're putting in a compressor, or the gas we're putting in the compressor, and the compressor is compressing it. You can think about your bicycle. If you pump air in your bicycle, the pump gets hot on the tip, yeah? So this is what a compressor is doing. It's compressing the gas, which already has taken over some energy from the environment, and then it's compressing it, so we get hotter gas and a hotter pressure. And this is then transported in another heat exchanger. You can see here, it's just an example. They can look a little bit different from other companies. And we are passing through now, through this heat exchanger, our water we want to heat up. Yeah, there's different ways you can do it. Just imagine there's water circulating now, and getting the heat from this heat exchanger and transferring it to our buffer tank and heating up the hot water inside. While we are doing this, this water which we were circulating here is cooling down, and then going back to the heat exchanger, that's a circuit. And then the gas inside, the hot gas, cools down, and then it becomes liquid again. It's a liquid gas. It's like a straight curve. It's a little bit strange, but it's becoming liquish, and then it will be transported into a expansion valve, and that will be handling the liquid gas like a fire spitter. If you have some alcohol in your mouth and you spit it out into a candlelight or something, it will evaporate, and this is what the valve is basically doing. And then we have vaporized gas again, and it is able to get energy from the environment again. It's an endless circle as long as the compressor is running. You don't have to refill gas. You don't have to do anything inside. It's just a physical process. And so we are able to transport energy from the outside air, in this case, to our gas, and the gas will transport the energy then to the compressor. The compressor is lifting it up on a higher temperature level. That temperature we can use to produce the hot water or the pool water or your heating demands while it's cooling down, doing this, and then it goes back in this circuit. Yeah. And this is basically how the heat pump works. And as I said at the beginning, in your fridge, if you open the fridge door and you put warm drinks in, you close the door, the little compressor in your fridge will get the energy out of your food or drinks and warms up the back at the fridge. Normally it's waste of energy, but as I always say to my wife, I put hot beer in, so I heat the kitchen for her. I think that makes sense. Okay, then a little bit more in detail now. This is the process as you find it in the normal drawings in every physics books, or if you ask Google or any search engine, or nowadays ChatGPT or whatever, you get pictures like this showing it. So you see there's the energy we're getting free from the air, from the ground, or from water. And then we transfer it into our heat pump. And on the other side, we have another transferring it to the house or to a buffer tank. And this is our heat source on the left, and the so-called heat sink on the right side here in the picture. And the whole process is evaporating the gas, compressing the gas, condensing the gas, and expanding the gas again, and then it starts over and over again. Now we're talking a little bit more in detail about the efficiency of a heat pump. There's the so-called COP and the SCOP. Most of you guys have heard, hopefully, about the COP, because it's on every marketing material in the world. If it's about heat pumps, you will find a COP. It's called coefficient of performance. And now, as marketeers are, they show the best they could find in their technical details. So often you find heat pumps showing we have a COP of 5 or we have a COP of 4. What does it mean? It means out of one part energy, in this case electrical energy, you can create, you put 4 parts of free energy, and you can give to the house or to the water tank an energy factor of 5. So 1 part you're paying for, 4 parts you're getting for free, 5 parts you can use later for your application. But that is just a momentum. If we're talking the real stuff, then you need to talk about the SCOP. The SCOP is basically the yearly, the seasonal performance factor. We are taking in all the tests the industry is doing. And if you're honest to your customers and in marketing, you have to show the SCOP, which is a little bit smaller or sometimes a little bit more smaller than the COP. The COP is a momentum. So at the moment we have in Johannesburg here 20 to 25 degrees. And we can now, if I produce a hot water flow towards the buffer tank of 50 degrees or 55 or 60, the COP might be 4.5 or 5. If it's 5 degrees outside, the COP is only 3.0 or 2.0, depending on the machine. But it's changing every second. The COP is basically changing. Yeah. So the trick is now to build a system which is able, especially in air source heat pumps, to cope with the different environmental temperatures from -20 or even -25 up to 40, 46 degrees, like in Kalahari. Yeah. And you have to look at the overall picture for the whole year. And there's a lot of changes, and that is measured in laboratories or in live measurements, and then put together as an SCOP. So basically, what have you put into your heat pump system over the whole year, including the circulation pumps, including the power for the controller, including everything, and then what could you gain from the environment, and what was the output? That is then your SCOP. So if you want to combine heat pumps or do a benchmark, and to really understand what heat pump is more efficient, which one, then you need to look at the SCOP. And some manufacturers, they hide it a little bit because they might be not that efficient at the minus degrees, while a company from Europe might be really efficient at minus degrees because that's their main market, right? I hope that makes sense so far. You see this here, the COP is going up, but over the whole year, you can see the SCOP might not be a 5 or a 6, it might be only a 3.9 or a 4 point or whatever. Simple formulas, I don't want to stress you too much in the afternoon. So you just have the free energy from the environment and what you need to put in work, like kilowatts or kilowatt hours or kilowatt per anno, and then you get your COP. That's pretty easy, but if you don't know it, you might buy a heat pump with a COP of 5, but at the end, it gives you only a SCOP of 2 or 3. Okay, so how can we heat hot water? And I thought about showing you hydraulics, but I think pictures are talking more. So there's different variations. You can have tank heat pumps, so-called integrated hot water heat pumps. The heat pump is on top, the tank is underneath, and the pipes you have seen earlier warming up the water, it's just warming up the water in the tank. Sometimes the pipes are around the tank or special heat exchangers. Sometimes the pipes for the heat exchange is in the tank. Then you have so-called monoblock heat pumps. They are just standing there and you connect 2 pipes towards your system. And this is all kind of different forms, sorts and forms, sizes from maybe 3 kilowatt up to 400 kilowatts. This is a typical installation in South Africa, but as you can see, it can vary a little bit from the bush to the sea. You can put them everywhere. For example, 300 liters, 200 liters, 400 liter heat pumps. It's enough for a house or a lodge setup or whatever you want. Pretty simple to install, like a normal geyser, yeah, with the vacuum breakers and everything. Every plumber can install it. You don't need to be a refrigerant expert or a HVAC expert. For bigger setups, we can build so-called cascades. Yeah, so the industry knows cascades very well. Instead of having one big heat pump, which will always start with, let's say, the maximum it can do. If your whole house needs at the coldest part in the year or at 5 degrees outside temperature, 50 kilowatts, a 50 kilowatt heat pump will always start with 50 kilowatt and then stops, 50 kilowatts and stops. So some some people in the industry, they build cascades. So we have a smaller one starting first. If it needs more power, the second one will come in and the third one will come in. And there's also so-called inverter heat pumps in the market. They do, in addition to this cascades, every heat pump can also give you a certain amount of kilowatts only, depending on how much your so-called heat sink or your water tank demands right now. There's heat pumps you can place inside the house, especially if we're talking areas like Camps Bay, where there's always air with salty water around. So from the outside, and this is for the architects within us, you only see the air grid where the air is going in, and then there's a special treatment on the evaporator that the salt cannot harm it, and then the heat pumps are inside, or if there's no space outside or on the roof, you can put the heat pumps in the basement, as well as the hot water tanks. You can build this, of course, bigger. This is an example of a hotel. There are 4 heat pumps inside, or 5 even here, with a cascade. Oh no, it's 4, it's a pipe. Sorry, my eyes are getting a little bit bad. And then the air is brought in with some air channels, but still there is a heat pump, a heat pump, a heat pump, a heat pump, and a tank. This is all you need, and some pumps and a controller. There's bigger heat pumps available, of course. You can place them outside or also inside or on the roof. This special t-shirt form is a European thing because it's raining a lot, especially in England, and it's not always that nice like in Johannesburg. So the rain cannot harm the evaporator and the technique inside, and it's really quiet. You see the air gets sucked in on the left side and pushed out on the right side down to the ground. And all the time when air is hitting the ground, it divides the decibel, the sound emission, by half. So it's really quiet. And in Europe or in bigger cities, you want to reduce the sound. You want to have sound of silence and not sound of heat pumps. That's why it's built like this. And because of maybe some snow laying around or coming down. So we have seen heat pumps where there's a meter of snow on top, but not in the heat pump. And for South Africa, this is a project we did in George. It's Eastern Cape, not Western Cape, as far as I know. And every house has a heat pump, and it's connected to a photovoltaic system. So the people living in these houses, they create the power for the heat pump for free. They use it basically as a third battery in this case, but the energy is stored in the hot water and not in this lithium or whatever batteries. I'm not an expert in PV. I don't know what batteries these are. You can go bigger, of course. Here's an example of a hotel setup with 199 rooms. And instead of using geysers with the heating element, there's now the use of heat pumps. And you see there a little bit in a house that there's no rain falling on it or whatever. The customer wanted it inside. It's also not a problem. On the other side, what you cannot see here, the environmental air is sucked in from the outside of the house, and then the exhaust air is just blown into this room here, but it doesn't do any harm. It's just air. Yeah. This is a student apartment in Johannesburg where there's a smaller setup with 6,000 liters hot water for a lot of student apartments, creating the hot water needs for the house. This is a hotel which I put in here. It's not an air source heat pump, it's a ground source heat pump. And for a source, we are using the return water from the chiller, which is normally called waste energy. So instead of going into a cooling tower and just being wasted, we are using it as a source. We are creating 30,000 liters of hot water for the hotel, while we are cooling down some water for the cooling in the house, and we could reduce the chiller size, the cooling tower size, by half. And whoever was in Swakopmund, even plastic is rusting away there. So our heat pumps are inside the house. Nothing can destroy them. It's a pretty cool system. We are busy building now also the same system, a little bit smaller, together with Michael's team in a clinic in Cape Town. This is some apartments, I think 30 apartments with 5,000 liters hot water in Johannesburg. It's near Killarney Mall. Then we have separate system here, again a heat pump in Windhoek, and the wind cannot harm our heat pump. So a heat pump wants to get air, but it doesn't want to get wind blowing the nice air away. So we are using always our machines which are pretty much covered, and also no cats can lay around on top They can, but they get not harmed by cold air. And this is for student accommodation with each 4,000 liters of hot water. And we have 12 of the systems, so 12 of these houses. And I think it's 25 apartments each, but I cannot remember in detail. Then what else you can do is you can build batteries of smaller ones. The redundancy is much more better. And instead of putting one big heat pump, you have now, for example, here, this surf camp, they have, I think it was 12 heat pumps, 12 times using only 500 watt, driven by electricity from the sun, is nearly running for free. That's a surf camp, and they do surfing here, not in the sea. Yeah. And these kind of batteries you can put in a container. You see our partner, they prepared it in their workshop, and then they delivered the container on site, and the plumber only had to connect flow and return to the container basically, and the cables, of course, from the PV system. And last but not least, it's the Cape Town Cape Gate Mediclinic, where we have also our heat pumps inside the roof, cooling down the air in the roof, that the chillers are running much more efficient, which are also in the roof. And these heat pumps producing the hot water for the Mediclinic there. And I can now hand over to Michael. Yeah, I think I stuck to my 20 minutes because Michael prepared the PVT system from the other side. And I can tell you so much that our heat pumps are nearly running for free. And Michael will explain how the PV system with the heat pump is running together. Thank you very much.
All right, guys, it's a very difficult act to follow after Ingo. Ingo is extremely well-knowledge and well-versed in heat pumps. And Ingo, thank you so much for joining us today and for adding so much value to the conversation. I really appreciate it. We appreciate your partnership over the last while as well. So guys, I'm just going to do a small little introduction to hybrid solar collectors, which are called PVT. So it's photovoltaic thermal. And as a first slide, I'd like to talk to you guys and just give you a brief example of various sectors that around the world and the energy consumption in those sectors. Now, we're going to be focusing this talk mostly around the built environment. So as we can see that the built environment consumes about 33% of the energy made available on an annual basis. About 15.5% of that energy is currently being produced through renewable resources, mainly solar PV. Industry, another 33% of consumption, 16.8% of that is being generated through renewable resources. And the remaining 33% is divided between transportation and agriculture. There's also a small amount of improvement or at least addition to solar PV or renewable resources to these type of sectors. Now, I'm going to focus on the built environment, and just as a matter of a question, I don't think anyone can answer, but if you had to give it a very high level idea, what would you think is electrical requirements in the built environment, or if you look at it on a percentage perspective? And it's actually going to shock you guys. Electricity requirements, electricity demand in the built environment generally equate to about 17%. Now, that is your TV, Wi-Fi, routers, washing machines, everything that requires electricity. Now, that only equates to about 17% of your annual demand. Now, the nice thing that I want to focus on below the waterline, as you can see, heating and cooling generally equate to 51% of your annual energy consumption. So if you had to think about your house, for example, where you've got an electric geyser or electric boiler, between 50 and 60% of your annual energy consumption can directly be linked to that electric boiler or electric geyser that's heating up your water. Now, the sad thing is that a lot of people go through the route of using the wrong technologies for the wrong application. So, for example, there's a massive drive in South Africa at the moment for renewables, seeing as load shedding is back, and we've had this problem with load shedding over the last couple of years, where you've seen that the PV uptake, PV and BESS or batteries uptake has increased drastically as a reason, well, to be able to meet the demand. Now, the problem with PV is, well, it's not really a problem, but the facts of PV, for every square meter of roof space that you currently have available in South Africa, there's about a kilowatt of energy that falls on that surface. But PV's only got an efficiency of 20%. So what does that mean? You've got 100% radiation that falls on the surface. And of that 100% radiation, 5% of that energy is lost due to reflection. And another 75% of the energy is actually lost to heat losses, which go through the top and the bottom of the panel. Now, what we know is that this heat also has a very detrimental impact to the production of the PV of the PV power or the PV laminate. So the warmer the panel becomes, the less efficient it becomes. So in real life application in South Africa, we can comfortably say that you're getting between 16 and 18% efficiency from your PV panel. Now, if you look at PVT, it's a thicker model. You've got a module, you've got 100% radiation that falls on the surface. We've got an efficiency of 19% on the PV side, so it produces the exact same equivalent of PV electricity as a panel of its size. But on top of that, we give you a 70% efficiency on the thermal aspect. Once you get 3% losses on reflection on the front of the collector, and you've got an 8% heat loss through the collector as well, thanks to the insulation. If you look at this collectively, you've got an 89% efficiency. Now, this is verified data, so these panels are Solar Key Mark approved. It's basically just to say that what we say is actually the truth. So as I said earlier, where you've got a kilowatt of energy that falls on your roof space, we can convert 89% of that back into two forms of energy, one being electricity, the other one being heat. I just want to take you through the evolution of this collector. So your standard solar PV panel was developed in the late 1950s. Once people started realizing that the heat had such a detrimental impact on the collector, but also that heat can be repurposed to meet your domestic hot water requirements, you started seeing the PVT0, which was just a PV collector with the heat recovery at the back. PVT1 had better rear insulation. PVT2 had a better front insulation on top of the rear insulation, and then the PVT3 AH technology is what I'm currently explaining to you guys at the moment, which is just an encapsulation of all of those. Right, and this is the layers of disposition. So you've got your front insulation, which is a glass front insulation. So for weathering purposes, it is a lot more durable. You've got your PV laminate or photovoltaic cells. Behind the PV laminate, we've got a heat recovery, which circulates glycol and distilled water in series through the back of the PV panel, extracting the heat from the PV laminate, ensuring that the electrical production is actually increased during the year. And what we're currently experiencing is that electrical performance could increase anywhere between 3 and 5% per annum. And then you've got rear insulation and you've got your frame. All right, so this collector has an 89% efficiency. We produce 380 watts of electricity on each collector and 1,370 watts of thermal energy per collector. It's the only panel, I can't say the only panel, but this panel has got the capacity to be able to produce both thermal energy and heat. These collectors are manufactured in Spain, and yet again, Solar Key Mark approved. All right, and these are a couple of our focus areas. Basically, we focus on any area where there's a high hot water demand. Our mission in our business is decarbonize hot water production through various sectors. We currently have got solutions installed on sports centers, district heating, retirement villages. We've got hospitals, private schools, and all sorts of different industrial applications as well. And I just wanted to show you guys. So this is the most profitable and effective solar panel in the world for the built environment and for industries. We produce four times more energy per square meter, directly reducing 4 times the amount of CO2, and our solutions are generally 3 times more profitable when you compare them to standard PV. As you can see, payback periods are roughly fairly the same, but the cost curve over the lifespan of the product increases 3-fold from your standard PV solution. All right, and Solarus Integrated Hot Water Solutions. So I'm just going to give you guys an example of how our solutions would look. PVTs produce both heat and electricity. Direct solar heat produced by the PVT can preheat water to as high as possible. We currently are able to produce hot water to about 75 degrees Celsius just using the thermal aspect on the PVT. The heat pumps heat the water further to the desired temperature if it's required. And electricity produced by the PVT can offset the heat pump consumption on an annual basis. PVTs can be integrated with any existing auxiliary and any new auxiliary heating system. And this is a rough design, or this is just a basic design to what our solutions would look like. So as you can see, you've got the Solarus PVT collector on the roof. There's a pump station controller. We usually fit this with a small battery as well. And remember I said to you that we circulate glycol and distilled water through the back of the collector into a closed loop system. So we actually replace the electrical element in these tanks with a solar loop. So we pump glycol and distilled water through the solar loop. So let's say, for example, we've got an array of 10 collectors in series or in parallel. There'll be a small circulation pump that pumps glycol and distilled water through this pump. It then goes into the solar preheat tank. Now, this preheat tank in summer, we can reach temperatures of about 75 degrees Celsius. From there, we've got a supply tank that's connected to a heat pump or your auxiliary. And if the temperature in the supply tank is below 60 degrees in the built environment, only then will the heat pump come on to keep this tank to 60 degrees Celsius. We've got a mixing valve, and then it goes out into the building. And this is generally your energy, your monthly heat and electricity delivered by the Solarus integrated solution. So we generally size the system for thermal or PVT to meet between 60 and 70% of the annual hot water demand using solar thermal. If we had to size it the opposite way around to meet 100% of the hot water demand in winter, the system would be extremely oversized for summer, which would then cause stagnation and the system would actually not be able to perform. So I'm just going to break down this first point. If you have a look at the screen on this graph, your yellow lines are the heat delivered by the PVT, and then your orange lines are the heat delivered by the auxiliary, which in this case is a heat pump. Heat pump consumes electricity, which is then highlighted by the red lines. Your red dots are the hot water demand on an annual basis, and your green lines are electricity produced by the PVT. So if you have a look on an annual basis, the electricity consumed by the heat pump is a lot less than what we are producing on the PVT on an annual basis. So in essence, once we've met the biggest demand that you have, which is hot water, you still have got excess PV electricity to go into the building to curb consumption after we've met and satisfied 100% of the hot water demand. Now, once you've included both PVT and the heat pump, we meet 100% of the hot water demand, so making it a 100% renewable hot water solution. PVT and heat pump heat balance. So as I said to you earlier, we generally size the system for the thermal or the PVT to meet about between 60 and 70% of the annual hot water production. The remaining 33% is met by the heat pump. But as you can see by the PVT and heat pump solution, the electricity balance, the electricity consumed by the heat pump, which is marked in the brown, is far less than electricity produced by the PVT. This is a project that we are currently busy working on in Cape Town. It's a 120-room hotel, very limited amount of roof space. The hotel's got 120 rooms, daily demand of 19,700 liters of hot water. Existing hot water system is 35,000 liter electric boilers, and currently paying an energy price of $1.99. So this hotel has got about just over 200 square meters of roof space available to deploy renewables. We ran a simulation comparing both PV and PVT systems so that we could give the client the most informative, or allow the client to make the most informative decision. So systems, as you can see, we've both suggested both a 100 PVT system or a 100 PV system. The hot water demand met by solar heat on the PVT system is between 60 and 70% on an annual basis. PV system will obviously be able to produce none of the heat required because it doesn't produce heat. Once you integrate the electricity produced on the PVT system into the electric boilers, it's 100% renewable hot water solution. But the PV system will only be able to produce 28% of the energy required to run those electric boilers on an annual basis. Now, what I would like to stress or just bring to your attention is the payback periods. Our system at a cost of about 3.3 million in comparison to a PV system of about 800,000, we pay back 6 months later, or will you break even? But the interesting part is that we produce 4 times more savings on that roof space compared to your standard PV. Our system will have estimated savings of about just over 26 million rand. PV system will save just about 6.6 million rand over a 25-year period. On top of that as well, we reduce 4 times the amount of CO2, where your PV system will reduce about 57,000 kgs of CO2 on an annual basis. Your PVT system will reduce about 218,000 kgs of CO2 on an annual basis. This is a couple of our proof of concepts, some installations taken from all around the world. So there's 102 PVTs on an Iberstar hotel in Tenerife in Spain. As you can see, what we initially predicted and compared to measured data, we are outperforming what we initially measured or predicted. There is an 88 PVT system for district heating in the Netherlands as well. What we predicted and what we measured, we are outperforming the predicted data by between 10 and 15% on an annual basis. Another proof of concept is the 66 PVTs on the Hilton Hotel in Cape Town, which is now the Hyatt. We are outperforming our initial predictions by between 15 and 20% on an annual basis. And then we've also got an installation, 88 PVTs on a cheese factory in the Netherlands, which is also producing between 10 and 15% better on an annual basis than what we initially predicted. All right, here's a couple of our clients and a couple of our references. We've currently got installations running on Hilton, Marriott, Novotel, Park Inn, Iberostar, District Heating in the Netherlands, Thermal Amir, Babylon is a hotel in the Netherlands, Strand Hotel, Henry Village, Mediclinic, Ilovo, Hyatt, De Bak Business Academy in the Netherlands, FD Hotels, and Regenerative. Another point that I just want to make, we have just completed over 356 installations of this PVT technology across 35 different countries. Right, guys, I was hoping that I'd be able to share some information from the Mediclinic project, but we have been asked not to share any data regarding that project with anyone. But what I can tell you is that we have done a project with Stiebel Altron where we have taken care of domestic hot water requirements at a private hospital in the Western Cape for Mediclinic. That system is outperforming our initial predictions. We've created a 100% renewable hot water solution. And thank you, Ingo, for his cooperation on this project and for all of the people that assisted us, Greenland Africa team, for example. Guys, thank you so much.
Great. Thank you so much. Thanks, Michael. Yeah, exciting stuff, guys. I think in a energy strapped country like ours, hot water demand is also massive, and this is really important work. This is the interesting part of the webinar where we get some discussion going. We got one or two questions lined up. So the first question that is in the chat box, Graham was asking a question around the seasonal COPs on the heat pumps in your systems, Michael.
Seasonal COPs. So as you can see, there was one slide that I showed you where the energy balance on an annual basis and how that deteriorates. So what we'd say in the summer months, we meet 100% of that demand with solar thermal. In the winter months, we can preheat water to as high as possible. So what we are currently seeing is that your grid water comes in at a temperature of between 16 and 18 degrees Celsius. If we preheat that in winter with PVT to 30, 35 degrees Celsius, to be able to get that delta from 35 to 50, for example, requires less work from the heat pump. So that's why we also increase the lifespan of that heat pump and increasing the COP of that heat pump at the same time. So I hope that answers your question, Graham.
That is 100% correct what you said, Michael. And then there's another question from Amy about the anomalies in the weather. If the temperatures drop down and the heat pump is running that moment, of course the energy it can gain from the environment is a little bit less, so it needs to work a little bit harder. And so, there's a thunderstorm here now in Joburg. I don't know. It's also with the efficiency of the heat pumps in the cold climate. Some of our heat pumps are built for the colder climates, so they work down to minus 20 degrees. This is where we set the boundaries. We have machines running in Finland, for example, but they are built for that. Yeah, so they run at a high efficiency even at minus temperatures, and this is all based then on the refrigerant circuit inside and on the technology we are using. You can create heat pumps for certain environments, but there's heat pumps you can use everywhere in the world. So some of our heat pumps, for example, running in Kalahari and in Botswana, and some are running in colder parts of Africa, yeah, in the north, in the desert. For example, in the desert, it gets really cold in the night, and during the day, there's like 40 degrees, and they do the same job. Of course, the efficiency will always vary, but then we have an inverter-controlled heat pump, so it will adjust the speed of the compressor only to the demand. Hope that answers the questions. So in the actual SCOP for the clinic building we have, it's just running since 3 months now or something, Michael. So we don't have the overall factor yet, but we can see that when we look at the COPs of a certain time period, like let's say only a week or a day, not a second, it's really high. So it's like 6 or 7 sometimes. And the one in Swakopmund, where we are using the source from the chiller, that is always running on 6, 7 point something, even higher. So the SCOP will be also around 5, 6-ish. So really high efficiency there.
Amazing, thanks. We got another question from Jackie. Would it be correct to say that PVT system is for large installations? A single dwelling, a house would not benefit. Michael, what's your thoughts?
Yeah, Jackie, so PVT can be implemented on a single dwelling household, for example, as well. It's just at the moment, because this technology is very new to the market, the cost factor is quite high. So especially taking into consideration that you require an auxiliary system like a heat pump, for example, on a residential application, we can't see that the financials actually make sense at the moment to actually roll out in a residential capacity. On a residential capacity, my advice would much rather be get PV and straight heat pump, and you're producing hot water for free, basically.
Mm-hmm. Then there's a question from Johan. The lifespan of the panels that Michael has to answer, and for the heat pumps, I can say we have heat pumps still running from the 80s. So if it's now, because you're asking for coastal conditions, there is companies in the market, they do the so-called coating of the heat pumps. So our heat pumps come out of manufacturing process already with a coated evaporator, which can handle a lot of dirt and stuff which is in the environment. But if it's about salt water or salt dust next to the Atlantic Ocean, let's say on Clifton Drive, then it needs a special coating that can cost between, let's say, 5 up to 10,000 rand maybe, and then the whole heat pump is not even coated from the outside, but also the evaporator, the PC board, everything will be sprayed, and then every year you need to check up on it, and it can last many years, yeah.
And on the on the PVT aspect, we give you, there's a lifespan of 25 years with an annual degradation factor of 0.96 on the PV laminate, and about 0.67% on the thermal element. So even after a 25-year period, if your system has been maintained properly, you should still have a 75% effective model as well.
And then Mike had a question about the positioning, I think, where to put the heat pump. Naya, if you have a big hotel, for example, instead of putting it maybe on the roof where it's a lot of wind sometimes, or it's getting colder, if you have a parking lot, a lot of companies nowadays putting it in the parking lot, for example, so the air inside is a little bit warmer already. So the warmer the source is, the better the heat pump is in terms of SCOP or COP. Yeah, so the efficiency is much more higher. So if you can hide it from the direct wind or something, but I can tell you that in South Africa, you can just place it everywhere. It's warm enough. Yeah, all the heat pumps can handle this. It's nice and warm here. That's why I live in Joburg. The question from Henk is for you, Michael. Yeah.
And then Henk, absolutely, PVT works extremely well at the temperatures when it comes to swimming pools. Obviously, the lower temperature requires, the more efficient the panel becomes. One of the largest solar thermal rooftop installations was done in Spain on an Olympic-size swimming pool arena with 1,040 PVT collectors on that roof, covering 100% of the thermal demand on that swimming pool. So it's definitely a great fit. And then Glenn, you've also got a question with regard for a school hostel. We're busy developing solutions now for a property developer in the Gauteng region for student housing, and these systems have got a payback period of under 4 years and a return of investment of over 1,000% over a 25-year period. So although the hostel is not occupied throughout the year, what we can do is we've got heat dissipators in place. So once we see that the heat actually is getting a little bit too much for the system to manage, we can disperse that heat remotely as well to ensure that the structural integrity of the solution is kept.
Then from Mark, if you have an existing system, of course, you can use it. We're doing a lot of retrofitting. If you have a tank there's always a place where you can put a sensor in, and otherwise we create a space where to stick it in, and it comes with the controllers. There's a possibility of a lot of sensors, and yes, you can switch off ESCOM. It's not that difficult because they're 90% off nowadays. So you don't use your ESCOM power anymore. You just link the cable to your heat pump. The heat pump will run on ESCOM power, or you have PV system, and then you save immediately, what, 70, 80%, whatever. I don't want to lie to you. That's why we stick in there, but I guess it's even more. And whatever geyser or tank you have, the most important part is, does it have a heat exchanger? How big is it? Is it only now a 300-liter geyser and you want to connect like a split heat pump to it? That is also possible. Or is it a 3,000-liter tank in your house or in an apartment building, or 5,000 liters? There's ways to connect a heat pump. There's always space for a heat pump or PV system somewhere, or PVT.
And then I think there was a question that we missed here from someone called Kitan Patel.
Yeah.
Yeah, your question was with regard to PVT system feasible for low-cost apartment complex. Definitely. I think when you're solving for such a big problem as the domestic hot water requirements, you mustn't really look at the financial commitment that takes up front. You have to have a look at the entire business case and what the value perspective is that we're adding. So as we're currently experiencing in South Africa, energy, especially our grid energy, is raising at a drastic rate on an annual basis. We're just going to be seeing another increment of about 12.74% over the next couple of weeks is going to be implemented. So when you're competing with an energy source like electricity, the business case and the financial parameters around these solutions are ridiculous, for lack of a better word. We've got some projects where your initial investment is about, like on bigger hotels and apartment blocks, your initial investment is between 3.5 and 4 million, but these solutions save between 76 and 80 million rand over a 25-year period. So we need to take those type of metrics into consideration as well. But we'd be more than happy to give you a complete cost-free or commitment-free assessment if you'd like to explore that as an avenue. Francois?
Thanks, guys. Question from my side around mechanisms of dealing with the capital expenditure. I know in the solar PV space, we saw companies that were able to own the PV system and sell you power. Are you aware of mechanisms like this taking shape in South Africa, where do you have any partners as yet that are able to absorb the capex and sell hot water to, for example, in a residential application?
Yeah, definitely. So firstly, Glenn, we've actually got Soltrain grants that we can tackle into.
Yes.
So Soltrain is a very good believer in their firm backing of PVT and heat pump technology, especially when these two technologies are working in symbiosis with one another. And to answer your question, Francois, we've got various finance parties on board that are jumping at the opportunity to finance heat purchase agreements, where we will calculate your current cost of heat on a kilowatt basis, and we will sell you back that heat 10 to 20% reduced to the cost of what you're currently experiencing. But another benefit on top of that is the fact that your actual increase on an annual basis is set to 5.5 or 6% or 7.5%, depending on the financier, where you're not exposed to the volatility of NERSA and ESCOM, is what we currently all are seeing increments of between 10 and 12% happen once or twice a year, for example. So those opportunities are available. We can explore the 10 years, so the lease agreement. So let's say, for example, we find a financier that will finance a solution of, let's say, 5 to 6 million rand. They will then have an internal rate of return that we need to meet. Once we meet that, they will own the facility for 10 years, selling you power at a reduced rate to ESCOM. And then thereafter, there's an exchange of a 1 rand coin, and that facility is yours for the last 15 years of that facility. For the period where the financier is involved, they take care of all the operation and maintenance of that facility, because it's their asset to maintain. Thereafter, the SLA will have to be your responsibility.
Mm-hmm. And then another sentence towards Glenn Howard. Also, the heat pumps we are using together with Solarus, we have the solar key mark as well. And in terms of PV, all the heat pumps are so-called smart grid or solar PV ready. So there is, for example, if you set your heat pump to a certain point of temperature you want to reach. If the sun is coming up and the inverters delivering enough power, it can tell the controller, and the controller will adjust the temperature to a higher level. So you can use PV thermal to heat up a tank. You can run the heat pump on PV systems with much higher if needed. So there's a lot of things you can put together.
Glenn, I just wanted to give you one last point on your Sol Train question. The projects that we currently are busy doing with Stiebel Altron on Mediclinics are also Sol Train granted.
Good. Everyone happy. And then
Okay,
thank you,
great.
Francois.
Thank you so much, gents.
Thank you, Francois.
No, thank you very much. And thanks everyone for listening. I know it's
Okay.
hard in the late afternoon.
And thank you to the Regenerative Collaborative of South Africa. Thank you so much for putting this together, guys. We really appreciate all of your involvement and for bringing us into this. It really means a lot. Thank you.
Pleasure. So before we finish up, a couple of important things on my end. Don't miss the next event in March, Greenwashing Exposed, the role of green labels and EPDs in the South African markets. Again, a massive thank you to the speakers for today. Thank you for sharing your knowledge. Thank you for the work you do. And we look forward to seeing what more you're going to do in the industry. A thank you to our sponsor as well, Solarus, for the webinar this afternoon. Then just a plug for an upcoming GreenEd course on design for greater efficiencies. If you're interested in doing a 101 course on green buildings, this is a 3-day course in March in Gauteng. There's still a few spaces left in April in Cape Town. And then a reminder, social media, don't forget to like us on social media, follow, like, and subscribe. It really helps attract sponsorships like the Solarus one that we got today. So that brings us to a close. Thank you so much for attending, guys. We hope you have a wonderful evening, and we'll see you again next month.